Have you ever wondered what it would be like to leave Earth behind, to pack up humanity and move to another world? Maybe you've seen movies about Mars colonies or heard billionaires talking about becoming a multi-planetary species. It sounds exciting, doesn't it? The idea of exploring new frontiers, of being pioneers on alien worlds. But here's something most people don't realize. We might be trapped. Today, we're going to explore why leaving Earth might be far more difficult than anyone wants to admit, and what the latest discoveries in astronomy and astrophysics tell us about our cosmic imprisonment. And one quick question: if you could only save one thing from Earth to take with you to another planet, what would it be and why? Let me know in the comments below. I will pin the most creative answer. Now let's begin. Let's start with something fundamental that most people take for granted: distance. When we talk about space travel in everyday conversation, we throw around terms like light years without really understanding what they mean. A light year isn't a measure of time, it's a measure of distance. It's how far light travels in 1 year. And light is fast, really fast. It moves at approximately 299,792,458 meters per second. In 1 year, light covers about 9,460,000,000,000 kilometers. That's a 9 with 12 zeros after it. Your brain probably can't even fully comprehend that number because human beings didn't evolve to think on cosmic scales. Now here's where it gets interesting. The closest star system to us, Alpha Centauri, sits roughly 4.37 light-years away. That means if you could somehow travel at the speed of light, which we'll talk about why you can't in a moment, it would still take you over 4 years just to reach our nearest neighbor. But we can't travel at light speed, not even close. The fastest spacecraft humans have ever built is the Parker Solar Probe, launched by NASA in 2018. At its peak velocity, it reaches about 690,000 kilometers per hour. That sounds incredibly fast, and it is by human standards. But at that speed, it would still take over 6,000 years to reach Alpha Centauri. 6,000 years ago, humans were just beginning to invent writing. Think about that. If our ancestors had launched a spacecraft back then, it would just now be arriving at the nearest star. But distance is only the first problem. Let's talk about something even more fundamental: the speed of light barrier. Albert Einstein's special theory of relativity, published in 1905, fundamentally changed how we understand motion, space, and time. One of the most important discoveries from this theory is that nothing with mass can reach the speed of light. As an object with mass approaches light speed, something strange happens. Its mass effectively increases, requiring more and more energy to continue accelerating. To actually reach light speed would require infinite energy, which is impossible. The universe has set a cosmic speed limit, and it's unbreakable according to our current understanding of physics. Some people argue, well, what about warp drives or wormholes? These concepts come from real physics, specifically from solutions to Einstein's field equations in general relativity. The Alcubierre drive, proposed by physicist Miguel Alcubierre in 1994, is a theoretical concept where space itself contracts in front of a spacecraft and expands behind it, allowing faster-than-light travel without actually breaking the light-speed barrier. Sounds perfect, right? Here's the catch. It would require exotic matter with negative mass or negative energy density. We've never observed such matter, and most physicists believe it doesn't exist. Even if it did, calculations suggest you'd need the energy equivalent of the entire mass of Jupiter just to send a small spacecraft across interstellar distances. That's not just impractical, that's essentially impossible with any technology we can currently imagine. Wormholes present similar problems. These theoretical tunnels through space-time could potentially connect distant parts of the universe, but they come with massive complications. First, we've never detected one. Second, they would require the same exotic matter to keep them stable and open. Third, Even if you could create and stabilize a wormhole, you'd need to already have both ends positioned where you want them, which means you'd have to get one end to your destination through conventional travel first. It's a chicken and egg problem on a cosmic scale. The mathematics works on paper, but the practical implementation remains firmly in the realm of science fiction. Now let's assume for a moment that we somehow solve the speed problem. Maybe we develop generation ships that can sustain human life for thousands of years, or we perfect cryogenic freezing, or we discover something new about physics that opens up possibilities we can't currently imagine. We still face another enormous challenge: radiation. Space is not the peaceful, empty void it appears to be. It's filled with deadly radiation coming from multiple sources. The sun constantly emits charged particles in what we call the solar wind. During solar flares and coronal mass ejections, this radiation intensifies dramatically. Beyond our solar system, cosmic rays, high-energy particles accelerated by supernovae and other violent cosmic events, zip through space at nearly light speed. When these particles strike atoms, they can tear through biological tissue, damaging DNA and increasing cancer risk. Here on Earth, we're protected by two crucial shields: our magnetic field and our atmosphere. Both of these work together to deflect or absorb most harmful radiation before it reaches us. When you leave Earth, you lose both of these protections. The astronauts aboard the International Space Station experience about 10 to 20 times more radiation than people on Earth's surface, even though they're still within Earth's magnetic field and only about 400 kilometers above the surface. On a journey to Mars, which takes roughly 7 months with current technology, astronauts would be exposed to radiation levels approximately 700 times higher than on Earth. Studies conducted by NASA and the European Space Agency have shown that this exposure significantly increases the risk of cancer, cataracts, and potential damage to the central nervous system. A round trip to Mars could expose astronauts to radiation doses approaching or exceeding currently recommended lifetime limits. If you're finding this fascinating and want to keep exploring the mysteries of our universe, hit that subscribe button and give this video a thumbs up. It really helps the channel grow and lets me know you want more content like this. Your support makes all the difference, but Mars is practically next door compared to interstellar destinations. On a multi-year or multi-generational journey to another star system, radiation exposure becomes one of the most serious obstacles to human survival. You can't just build thicker walls on your spacecraft either. Adding shielding adds mass, which requires more fuel, which adds more mass, creating a vicious cycle. Some researchers have proposed using water or hydrogen-rich materials as shielding, since hydrogen atoms are particularly good at absorbing radiation. Others have suggested creating artificial magnetic fields around spacecraft, but all of these solutions require technology far beyond what we currently possess, and they all come with enormous energy requirements. Here's something even more sobering. Radiation isn't just dangerous to humans, it's dangerous to all the equipment and systems that would keep humans alive during a long space journey. Electronic components degrade when exposed to high-energy particles. Solar panels lose efficiency. Computer systems can experience errors or failures. The longer the journey, the more likely critical systems will fail. And in the void of space, there's no rescue mission coming if something goes wrong. You're truly on your own, millions or billions of kilometers from help. Let's talk about another challenge that doesn't get enough attention: resources. Human beings need food, water, and oxygen to survive. On Earth, these are provided by complex ecosystems that have evolved over billions of years. Plants produce oxygen through photosynthesis. The water cycle constantly recycles water through evaporation, precipitation, and filtration. Soil microorganisms break down waste and create nutrients for plants. It's an incredibly sophisticated system, and we're still discovering how all the pieces fit together. Replicating even a tiny fraction of this system in a closed environment on a spacecraft is extraordinarily difficult. The International Space Station recycles about 93% of its water, which sounds impressive until you realize that the remaining 7% must be resupplied from Earth. The ISS is only 400 kilometers away, making resupply missions relatively straightforward. Imagine trying to maintain a closed-loop life support system for decades or centuries with no possibility of resupply. Every single component must work perfectly, or people die. There's no margin for error, no backup plan, no emergency shipment arriving next month. NASA and other space agencies have conducted numerous experiments on closed ecological systems. One of the most famous was Biosphere 2, a facility in Arizona that attempted to create a completely sealed ecosystem in the early 1990s. Despite enormous resources and planning, the project encountered serious problems. Oxygen levels dropped unexpectedly due to microbes in the soil consuming more than anticipated. Carbon dioxide fluctuated wildly. Certain species died out while others proliferated beyond control. And this was here on Earth, where help was always available if things went catastrophically wrong. The experiment revealed just how little we understand about maintaining artificial ecosystems. Growing food in space presents its own set of challenges. Plants need light, water, nutrients, and the right atmosphere to grow. They also need gravity, or at least they've evolved to use gravity for important processes like directing root growth and distributing water and nutrients. In microgravity or low-gravity environments, plant growth becomes unpredictable. Researchers on the ISS have successfully grown lettuce, radishes, and other crops in specialized chambers, but these are small-scale experiments. Scaling up to feed an entire crew for years requires enormous amounts of space, energy for lighting, and careful management of every environmental variable. Then there's the psychological factor. Human beings evolved in wide-open spaces with access to nature, varied environments, and complex social structures. Confining people to a small metal box for years or decades takes an enormous psychological toll. Antarctic research stations provide some insight into this. Scientists who spend long periods at isolated Antarctic bases report depression, interpersonal conflicts, sleep disturbances, and cognitive difficulties, despite being carefully selected and trained. Some Antarctic stations experience what researchers call the third quarter phenomenon, where morale drops most severely about 3/4 of the way through a long stay. Now imagine that instead of Antarctica, you're in a spacecraft where you can't go outside, can't breathe fresh air, and can't see anything but the same walls and the same small group of people for years on end. Speaking of Mars, the challenges I'm describing become even more extreme when we consider actually living on another planet rather than just traveling through space. If you want to understand the specific obstacles we'd face trying to establish a permanent presence on the red planet, I've created another video called "This is Why We Would Never Survive on Mars," where I break down everything from the toxic soil to the communication delays with Earth. You'll see why even our closest planetary neighbor presents almost insurmountable challenges for human settlement. But for now, let's continue exploring why leaving Earth's vicinity is so fundamentally difficult. One aspect of space travel that science fiction often ignores is the issue of propulsion and fuel. Getting anything into space requires enormous amounts of energy. The tyranny of the rocket equation, first formulated by Konstantin Tsiolkovsky in 1897, shows us why. The basic principle is this: to go faster, you need more fuel. But more fuel means more mass. More mass means you need even more fuel to accelerate that mass, which adds more mass, requiring more fuel, and so on. The relationship isn't linear, it's exponential. This is why rockets are mostly fuel. The Saturn V rocket that sent astronauts to the Moon weighed approximately 3,000 metric tons at launch. Of that, only about 45 metric tons was the actual payload that reached the Moon, less than 2% of the total mass. Everything else was fuel, engines, and tanks that were discarded along the way. And the Moon is close, cosmically speaking. It's only about 384,000 kilometers away. Sending humans to Mars, which at its closest approach is about 55 million kilometers away, requires vastly more fuel. Sending humans to another star system? The fuel requirements become astronomical, literally. Various propulsion concepts have been proposed to address this challenge. Ion drives, which use electricity to accelerate ions to high speeds, are far more efficient than chemical rockets but produce very little thrust. The Dawn spacecraft, which explored the asteroid Vesta and the dwarf planet Ceres between 2011 and 2018, used ion propulsion. It worked beautifully for an unmanned probe, but ion drives currently can't generate enough thrust to be practical for large crewed spacecraft, especially for escaping Earth's gravity well. Nuclear propulsion has been discussed since the 1950s. The concept is straightforward. Use the enormous energy from nuclear fission or fusion to heat propellant and expel it at high speeds. This could theoretically provide much better performance than chemical rockets. Project Orion, studied in the late 1950s and early 1960s, proposed using nuclear explosions to propel a spacecraft, literally dropping atomic bombs behind the ship and riding the shockwave. Calculations suggested it could reach a few % of light speed, making interstellar travel theoretically possible within human lifetimes. The project was abandoned for obvious reasons. It would require detonating thousands of nuclear weapons, violating the Partial Test Ban Treaty of 1963, and creating massive radioactive contamination. More recently, scientists have explored concepts like nuclear thermal rockets, which use a nuclear reactor to heat hydrogen propellant, and nuclear electric propulsion, which uses a reactor to generate electricity for ion drives. NASA has invested in researching these technologies, and they show promise for missions within our solar system. But even with nuclear propulsion, interstellar travel remains extraordinarily difficult. The amount of fuel needed, the shielding required to protect humans from the reactor, and the complexity of the systems all compound the challenges we've already discussed. Solar sails represent another interesting concept. These would use the pressure from sunlight or light from powerful lasers to gradually accelerate a spacecraft. Since they don't carry fuel, they avoid the rocket equation problem. The Planetary Society's Light Sail, 2 spacecraft launched in 2019, successfully demonstrated controlled solar sailing in Earth orbit. For interstellar missions, scientists have proposed the Breakthrough Starshot initiative, which would use powerful ground-based lasers to push tiny spacecraft with large sails to perhaps 20% of light speed. This could potentially reach Alpha Centauri in about 20 years. However, there's a catch. The spacecraft would be tiny, perhaps only a few grams carrying minimal instruments, certainly nothing that could support human life. And there's no way to slow down once you get there. You'd just zip past your destination at enormous speed. Let's shift to another fundamental problem: communication. We're used to instant communication here on Earth. You send a text message, and it arrives in seconds or less regardless of where the recipient is on the planet. But in space, communication is limited by the speed of light. Light, and therefore radio signals, takes about 1.3 seconds to travel from Earth to the Moon. That's why there were slight pauses in conversations between mission control and the Apollo astronauts. Talking to someone on Mars involves delays of anywhere from 3 to 22 minutes each way, depending on where Earth and Mars are in their orbits. Now imagine you're traveling to Alpha Centauri over 4 light years away. If you send a message home, it takes over 4 years to arrive. If someone responds immediately, their reply takes another 4 years to reach you. You'd be receiving news about events that happened 8 years in the past. If something goes wrong and you need help or advice from Earth, you're completely on your own. This communication lag doesn't just affect morale and connection to home, it has serious practical implications. Mission control can't help you troubleshoot problems. Doctors on Earth can't provide medical guidance for emergencies. You're utterly isolated, more isolated than any humans have ever been in our entire history. There's also the question of navigation. Here on Earth, we use GPS satellites to determine our position with incredible accuracy. GPS works by receiving signals from multiple satellites and calculating your position based on the time it takes those signals to reach you. In deep space, there's no such system. Navigating requires careful observations of stars and other celestial objects, combined with precise calculations. The farther you travel, the more difficult navigation becomes. Small errors early in a journey compound over time and distance. Miss your target by a tiny fraction of a degree, and you could end up millions of kilometers off course. The New Horizons spacecraft, which flew past Pluto in July 2015, required incredibly precise navigation to reach its target after a journey of over 9 years and nearly 5 billion kilometers. Teams of engineers constantly monitored its trajectory and made tiny adjustments along the way. Even with all that expertise and attention, the spacecraft was only about 1 minute ahead of schedule when it reached Pluto, demonstrating both the precision achieved and how critical timing is in space travel. For a crewed interstellar mission lasting decades or centuries, maintaining that level of precision becomes exponentially more challenging. Now let's talk about something even more unsettling: time itself. We've already discussed how the speed of light limits our travel, but it also warps time in ways that make long-distance space travel even more complicated. Einstein's theory of relativity tells us that time isn't constant. It stretches and compresses depending on how fast you're moving and how strong gravity is around you. This isn't just theoretical. We've measured it with atomic clocks on fast-moving jets and satellites. Here's the problem. If you travel at near light speed to reach another star system, time for you would pass much slower than it does for people back on Earth. This is called time dilation. For example, if you travel to Alpha Centauri at 90% the speed of light, the trip might take about 5 years for you, but back on Earth, over 10 years would have passed. Your friends, family, and even the civilization you left behind would have aged more than you. If you returned, you might find that everyone you knew was gone. This isn't just a plot device from science fiction, it's a real consequence of physics. The faster you go, the more extreme the effect. At 99% the speed of light, a one-way trip to Alpha Centauri would take about 4.5 years for the traveler, but nearly 6 years would pass on Earth. At 99.99% light speed, the traveler might experience only a few months, while decades or even centuries could pass back home. You'd be a time traveler, but not in the way you might hope. This creates a psychological and social nightmare. Would you leave Earth knowing you might never see your loved ones again? Would you be willing to return to a world that's moved on without you? And what if something goes wrong? If your ship breaks down, you can't just call for help. You're stranded in the void, with no way to communicate with a home that may no longer exist as you remember it. But let's say we somehow solve all these problems: propulsion, radiation, time dilation, communication. There's still one more obstacle that might be the most insurmountable of all: the sheer scale of the universe. The distances between stars aren't just big, they're unimaginably big. Even if we could travel at light speed, the universe is so vast that reaching even the nearest stars would take years, and crossing our own galaxy would take hundreds of thousands of years. Our Milky Way galaxy is about 100,000 light-years across. That means even at light speed, it would take 100,000 years to go from one side to the other. and our galaxy is just one of trillions in the observable universe. The Andromeda Galaxy, our nearest large neighbor, is 2.5 million light-years away. If we sent a message there today, it wouldn't arrive for 2.5 million years, and any reply would take another 2.5 million years to get back. By then, humanity might not even exist anymore. This isn't just a problem of distance, it's a problem of time. The universe is old, really old. The Big Bang happened about 13.8 billion years ago. Earth formed about 4.5 billion years ago. Humans have only been around for a few 100,000 years. Civilizations rise and fall in the blink of a cosmic eye. If intelligent life exists elsewhere in the universe, the odds of two civilizations existing at the same time and being close enough to communicate are astronomically small. This is known as the Fermi paradox. If the universe is so vast and old, where is everybody? One possible answer is that the distances are simply too great. Even if intelligent civilizations exist, they might be too far away to ever find each other. We could be shouting into the void forever, and no one would ever hear us. But let's bring this back to Earth for a moment. If leaving our planet is so difficult, if the universe itself seems designed to keep us here, what does that mean for us? Are we doomed to be a single-planet species forever? Or is there another way to think about our place in the cosmos? Here's the thing, maybe we're not meant to leave Earth. Maybe we're meant to protect it. Our planet is the only home we've ever known, and it's the only place in the universe where we know life exists. It's a rare, precious oasis in a vast, hostile cosmos. Instead of dreaming about escaping to other worlds, perhaps we should focus on preserving the one we have. That doesn't mean we should stop exploring. Robotic missions, telescopes, and scientific research help us understand the universe and our place in it. But when it comes to human spaceflight, maybe we should be more realistic about our limitations. The Moon and Mars might be within our reach, but beyond that, the challenges are so immense that they might be insurmountable with any technology we can currently imagine. If you've made it this far, you're clearly someone who loves thinking about the big questions. If you want to dive deeper into why Mars might be a dead end for human colonization, check out my video, This is Why We Would Never Survive on Mars. It breaks down the toxic soil, the radiation, the lack of atmosphere, and all the other reasons why the red planet might be a one-way trip with no return. The link is in the description and on the card above. And if you're enjoying this journey through the cosmos, don't forget to hit that subscribe button and give this video a thumbs up. It really helps the channel grow, and it lets me know you want more content like this. Your support means everything. Let's explore another challenge that doesn't get discussed enough: gravity, or rather, the lack of it. Human bodies evolved over millions of years in Earth's gravitational field. Every system in our body, our bones, muscles, heart, digestive system, even our inner ear, is calibrated for one specific gravitational environment. When you remove gravity, everything starts to break down. Astronauts on the International Space Station experience microgravity, and the effects on their bodies are severe. Bone density decreases by about 1 to 2% per month in space. That might not sound like much, but over a year, you could lose up to 24% of your bone mass. That's comparable to severe osteoporosis. Your bones literally dissolve because they're not under the constant stress that tells them to stay strong. Muscles atrophy too, including the heart, which doesn't have to work as hard to pump blood without gravity pulling it down. The astronaut Scott Kelly spent 340 days aboard the ISS from 2015 to 2016 as part of NASA's twin study, where his identical twin Mark remained on Earth for comparison. When Scott returned, scientists found that his telomeres, the protective caps on the ends of chromosomes, had actually lengthened in space, which was unexpected. but they quickly shortened again after returning to Earth, and some ended up shorter than before. His immune system was altered. His carotid artery thickened, his gut bacteria changed significantly. Vision problems developed because fluid shifted toward his head without gravity to distribute it properly throughout his body, and Scott was only in space for less than a year. Imagine what happens on a multi-year journey to another star system. Even if you create artificial gravity by rotating your spacecraft, which is theoretically possible but engineering-wise extremely complex, you'd need a massive structure. The rotation would create Coriolis effects, apparent forces that would make moving around feel strange and disorienting. Drop something and instead of falling straight down, it would curve. Turn your head quickly and you'd feel dizzy. Your inner ear, which helps maintain balance, would constantly receive confusing signals. Mars presents a different problem. Its gravity is only about 38% of Earth's. We have no idea what prolonged exposure to partial gravity does to the human body because we've never tested it. Will it be enough to prevent bone loss and muscle atrophy? Will children born on Mars develop properly? Their bones might grow differently, their muscles might not develop the same strength, their cardiovascular systems might adapt to the lower gravity. If that happens, could they ever return to Earth? Would Earth's gravity be too strong for them, crushing their weaker bones and overtaxing their hearts? These aren't just medical curiosities, they're fundamental questions about whether humans can truly become a multi-planetary species. We might biologically be tied to Earth in ways we don't fully understand yet. Our bodies might simply not be capable of thriving anywhere else in the universe. Let's talk about another issue that keeps me up at night: cosmic debris. Space isn't empty. It's filled with dust, rocks, and countless objects moving at tremendous speeds. Here in our solar system, we're somewhat protected. We've mapped most of the large asteroids, and Jupiter's massive gravity acts like a cosmic vacuum cleaner, pulling in many objects that might otherwise threaten Earth. But in interstellar space, you're traveling through unknown territory at enormous speeds. Even a tiny particle becomes deadly at relativistic speeds, speeds approaching the speed of light. Imagine your spacecraft traveling at 10% of light speed, which is about 30,000 kilometers per second. A grain of sand hitting your ship at that velocity would release energy comparable to a large bomb. The kinetic energy of an object increases with the square of its velocity, so doubling your speed quadruples the destructive power of any collision. At near light speeds, even individual atoms hitting your ship could cause significant damage. There's no practical way to shield against this. You can't see these particles coming in time to dodge them. Light from the particle only reaches you at the same time the particle does. You could build thicker armor, but remember the rocket equation problem. More mass means more fuel, which means more mass, spiraling into impossibility. Some scientists have proposed using powerful magnetic fields to deflect charged particles, or placing sacrificial shields ahead of the spacecraft to absorb impacts. But these solutions are theoretical, unproven, and come with their own massive engineering challenges. The Voyager 1 spacecraft, launched in September 1977, is now the most distant human-made object from Earth, over 23 billion kilometers away. It's traveling at about 17 kilometers per second relative to the Sun. At that speed, it would take over 70,000 years to reach the nearest star, and that's assuming it were heading in the right direction, which it isn't. In all its decades of travel through interplanetary and now interstellar space, Voyager has been lucky enough not to hit any significant debris. But it's tiny, and it's moving relatively slowly compared to the speeds we'd need for practical interstellar travel. The faster and larger we go, the more likely catastrophic collisions become. Here's something else to consider: isolation from Earth's biosphere. Humans didn't evolve alone. We co-evolve with countless microorganisms, plants, and animals. Your body contains trillions of bacteria, fungi, and other microbes. In fact, microbial cells outnumber your own cells. These organisms aren't just passengers, they're essential to your health. They help digest food, produce vitamins, train your immune system, and even influence your mood and behavior through the gut-brain connection. In a sealed spacecraft, this delicate microbial ecosystem would change over time. Some species would thrive, others would die out. New strains might evolve in the isolated environment. Research on the ISS has shown that bacteria can become more virulent in space, growing faster and becoming more resistant to antibiotics. Without the constant influx of new environmental microbes that we encounter on Earth, your microbiome would drift into unknown territory. We don't know what long-term effects this would have, but it's reasonable to assume they wouldn't all be positive. Plants face similar challenges. Most plants rely on complex relationships with soil microorganisms, mycorrhizal fungi that help their roots absorb nutrients, nitrogen-fixing bacteria, decomposers that break down organic matter. Recreating this incredibly complex underground ecosystem in a spacecraft is extraordinarily difficult. Those experiments I mentioned earlier on the ISS grow plants in carefully controlled hydroponic systems, but these are nothing like natural soil ecosystems. Scaling them up to provide food for a crew over years or decades remains an unsolved problem. Then there's the issue of genetic diversity. For a viable population that can sustain itself over many generations, you need genetic diversity to avoid inbreeding and maintain the health of the population. Population geneticists estimate that you'd need at least several hundred individuals, possibly thousands, to maintain a healthy gene pool over the long term. That's a lot of people to cram into a spacecraft, requiring enormous amounts of food, water, oxygen, and living space. The engineering challenges multiply with every additional person. Some people suggest sending frozen embryos or genetic material instead, reducing the number of initial travelers. But this raises its own questions. Who would raise the children? How would culture and knowledge be transmitted? Would these children, born in the void between stars, have any connection to Earth or humanity as we know it? They'd be truly alone, more isolated than any humans in history, with no planet to call home. Let's consider the economics for a moment. Space travel is expensive, really expensive. The Apollo program, which sent 12 humans to the moon between 1969 and 1972, cost approximately $25 billion at the time, equivalent to over $150 billion today when adjusted for inflation. And that was just for short trips to our nearest celestial neighbor. The International Space Station has cost roughly $150 billion over its lifetime, and it's only 400 kilometers above Earth. Sending humans to Mars would cost hundreds of billions, possibly trillions of dollars. An interstellar mission, the costs would be almost incomprehensible. You'd need to develop entirely new technologies, build enormous spacecraft, create closed-loop, life support systems that work for decades or centuries, solve the radiation problem, develop new propulsion systems. All of this would require resources on a scale that might exceed the entire global economy. Who would pay for it? What government or organization could justify spending that much money on a project that wouldn't yield results for generations or centuries? And even if someone did fund it, what would be the return on investment? You can't mine resources from another star system and bring them back. The round trip would take thousands of years. There's no economic incentive, only the abstract goal of exploration and survival. This brings us to a profound philosophical question. Is the dream of leaving Earth really about survival, or is it about something else entirely? When we talk about becoming a multiplanetary species, we often frame it as a backup plan. If something catastrophic happens to Earth, an asteroid impact, nuclear war, climate disaster, or some other existential threat, humanity would survive elsewhere. But this logic has a fundamental flaw. Any catastrophe that makes Earth uninhabitable would still leave us with a planet that's far more hospitable than anywhere else in the solar system, let alone the universe. Even if Earth experienced a global nuclear war, devastating climate change, or a massive asteroid impact, it would still have a breathable atmosphere, liquid water, a protective magnetic field, and appropriate gravity. Mars has none of these things. Venus is a hellish world with surface temperatures hot enough to melt lead and atmospheric pressure that would crush you instantly. The moons of Jupiter and Saturn are frozen wastelands billions of kilometers from the Sun. If we have the technology to survive on Mars, to create habitats, generate oxygen, grow food, and shield ourselves from radiation, then we certainly have the technology to survive on a damaged Earth. It would be far easier to build underground cities on Earth than enclosed habitats on Mars. It would be simpler to filter Earth's polluted atmosphere than to generate breathable air from Martian carbon dioxide. Any scenario where Mars becomes a refuge is a scenario where Earth, even in its worst state, would still be the better option. So maybe the drive to leave Earth isn't really about survival. Maybe it's about something deeper in human nature, the desire to explore, to push boundaries, to see what's beyond the next horizon. Our ancestors left Africa and spread across the globe, crossed oceans in fragile boats, climbed the highest mountains, and dove to the deepest ocean trenches. Exploration is part of who we are as a species. The question is whether that drive is enough to overcome the practically insurmountable obstacles the universe has placed in our path. Let me share something that makes this even more humbling. The observable universe is just a tiny fraction of the entire universe. Because the universe is expanding and that expansion is accelerating, there are parts of the universe we will never be able to reach, no matter how advanced our technology becomes. The cosmic horizon is about 46 billion light-years away in all directions. Beyond that, space is expanding faster than light can travel through it. Objects beyond that horizon are moving away from us so quickly that their light will never reach us. They're forever beyond our grasp. Even within the observable universe, the acceleration of cosmic expansion means that distant galaxies are slipping away from us. In fact, calculations by cosmologist Lawrence Krauss and others have shown that billions of years from now, only our local group of galaxies, the Milky Way, Andromeda, and a few dozen smaller galaxies gravitationally bound together, will be visible from Earth. Everything else will have receded beyond the cosmic horizon. Future civilizations, if they exist, might look out into space and see only their local galaxy cluster, thinking the universe is much smaller than it actually is. This means we're living in a special time, cosmologically speaking. We can see evidence of the Big Bang in the cosmic microwave background radiation. We can observe distant galaxies and study the universe's expansion. But this window won't stay open forever. The universe itself is pulling away from us, ensuring that we'll be forever confined not just to our planet or our solar system, but eventually to our local cosmic neighborhood. There's another aspect of cosmic scale that's worth considering: the age of the universe and our place in time. The universe is 13.8 billion years old. Our Sun is about 4.6 billion years old, meaning it formed when the universe was already over 9 billion years old. Stars could have had planets with life billions of years before Earth even existed. If intelligent life arose on any of those worlds, those civilizations could have had a billions of years head start on us. Think about human technological progress. We went from the first powered flight by the Wright brothers in 1903 to landing on the moon in 1969, just 66 years. We went from room-sized computers to smartphones that fit in your pocket in a few decades. Now imagine a civilization that had not decades or centuries, but millions or billions of years to develop. If such a civilization exists or existed, their technology would be so advanced that we couldn't even comprehend it. They would appear godlike to us. So where are they? This is another facet of the Fermi paradox. If advanced civilizations have had billions of years to develop, why haven't they colonized the galaxy? Our galaxy is about 13 billion years old. Even traveling at a small fraction of light speed, a civilization could colonize every star system in the Milky Way in just a few million years, a blink of an eye on cosmic timescales. Yet we see no evidence of such colonization, no megastructures, no radio signals, no signs of intelligent modification of star systems. The galaxy appears completely natural, untouched by advanced intelligence. One possible explanation is the Great Filter hypothesis proposed by economist Robin Hanson in 1996. The idea is that somewhere between the emergence of life and becoming an advanced, spacefaring civilization, there's a barrier, a filter, that almost no species passes through. Maybe life itself is incredibly rare. Maybe the jump from simple single-celled life to complex multicellular life is nearly impossible. Maybe intelligence rarely evolves, or when it does, civilizations tend to destroy themselves before they can spread to the stars. Here's the unsettling part. We don't know where the Great Filter is. If it's behind us, if the hard step was the origin of life, or the evolution of complex cells, or the development of intelligence, then we're extraordinarily lucky to be here, but the future looks bright. We might be alone in the galaxy, free to explore and expand. But if the Great Filter is ahead of us, that's terrifying. It would mean that something catastrophic tends to happen to civilizations at roughly our level of development. Nuclear war, environmental collapse, artificial intelligence going wrong, engineered pathogens. Something prevents species like us from reaching the stars. The silence of the universe might be telling us something important. Leaving your home world and spreading across the galaxy might be fundamentally impossible, or at least so difficult that no one has managed it yet. The physics of the universe, the vast distances, the speed of light barrier, the radiation, the energy requirements might constitute an insurmountable wall that keeps every civilization confined to its planet of origin. But there's another interpretation of the Fermi paradox that I find both beautiful and sobering. Maybe advanced civilizations choose not to expand across the galaxy. Maybe once a species reaches a certain level of maturity and wisdom, they realize that their home world is precious beyond measure and that exploring the universe doesn't require physically going there. Perhaps they perfect virtual reality, allowing them to explore simulated universes limited only by imagination. Perhaps they turn their attention inward, exploring consciousness, art, philosophy, and the mysteries of their own existence rather than the physical cosmos. Or perhaps they recognize that life is rare and precious, and the ethical thing to do is preserve and protect it where it exists rather than spreading and potentially contaminating other worlds. Earth's biosphere has taken billions of years to evolve. Every species here is unique, the product of an unbroken chain of evolution stretching back to the origin of life itself. Taking bacteria or other microorganisms to Mars or other worlds could contaminate those environments, potentially destroying any native life that might exist there, or making it impossible for us to ever know if life arose independently. This is why NASA and other space agencies have strict planetary protection protocols. The Mars rovers are carefully sterilized before launch to minimize the risk of contaminating Mars with Earth life. When the Cassini spacecraft's mission to Saturn ended in September 2017, NASA deliberately crashed it into Saturn's atmosphere rather than risk it eventually colliding with one of Saturn's potentially habitable moons, like Enceladus or Titan. Protecting the pristine environments of other worlds is taken seriously, even though it limits what we can do. There's a concept in ecology called the island biogeography theory, developed by ecologists Robert MacArthur and Edward Wilson in the 1960s. It examines how species diversity on islands is affected by the island's size and distance from the mainland. Smaller islands support fewer species. More distant islands are harder for species to reach, so they have less diversity. When an island becomes too isolated or too small, populations can't sustain themselves and eventually die out. Now think of Earth as an island in the vast ocean of space. We're isolated by distances so enormous that reaching even the nearest islands, other star systems, requires technology we don't possess and may never develop. Our island is rich with life, but it's alone. The question is whether we can sustain ourselves here indefinitely, or whether our isolation ultimately dooms us. The paleontological record shows us that extinction is the norm. Over 99% of all species that have ever lived on Earth are now extinct. Some went extinct gradually, outcompeted by other species or unable to adapt to changing environments. Others disappeared suddenly in mass extinction events. Earth has experienced 5 major mass extinctions in the past 540 million years. The most severe was the Permian-Triassic extinction about 252 million years ago, which wiped out roughly 96% of marine species and 70% of terrestrial species. The most famous is the Cretaceous-Paleogene extinction 66 million years ago, which ended the age of dinosaurs. An asteroid approximately 10 to 15 kilometers wide struck what is now the Yucatan Peninsula in Mexico, releasing energy equivalent to billions of atomic bombs. The impact triggered global wildfires, massive tsunamis, and threw so much dust and debris into the atmosphere that it blocked out the sun for years, collapsing food chains worldwide. The scary thing about that dinosaur killer impact isn't just that it happened, it's that it proves a simple point. Earth is not perfectly safe. Space can reach into your living room, even from millions of kilometers away, and change the whole story of life in a single day. But here's the twist. This is where a lot of "we need to leave Earth" talk starts, and where the logic often breaks. If your goal is to survive big disasters, your best move is not packing up and running to Mars or beyond. Your best move is learning how to see danger early, preparing smart defenses, and keeping your one working biosphere healthy. Because even after a catastrophe, Earth is still the only place we know that already has everything you need: air pressure you can live in, a water cycle, a magnetic field, and an ecosystem that makes food and oxygen without you babysitting it every second. So what can you actually do as a species to deal with threats from space? First, you watch the sky like your future depends on it. Because it does. You already have real missions doing this. NASA's Near-Earth Object Program tracks asteroids and comets that pass near Earth, using ground-based observatories and space telescopes. One example is NEOWISE, a NASA mission that searched for asteroids using infrared light. Infrared matters because dark rocks can hide invisible light, but they still glow with heat in infrared. That's a big deal when you're trying to spot something sneaking in from the dark. NASA NEOWISE mission pages. You also have major survey telescopes on the ground that scan huge areas of sky again and again, looking for anything that moved. This is not glamorous work. It's patient, careful, and constant, but it's the difference between surprise and warning. Second, if you find a threat, you test ways to nudge it. This isn't a movie anymore. In September 2022, NASA's DART mission slammed into a small asteroid moon called Dimorphos to test whether a kinetic impact could change its orbit. It worked. After the impact, the orbital period changed by tens of minutes, showing that a spacecraft can measurably deflect an asteroid in a controlled way. That's not a full planetary shield, and it won't solve every scenario, but it's proof that you're not helpless. NASA DART results. Notice what's happening here. The most realistic Planet B plan isn't running away. It's getting better at protecting Planet A. And this connects to a deeper reason you can't just leave Earth like it's a bad apartment. Earth is not a location. It's a life support system. It's a working machine made of oceans, rocks, clouds, microbes, forests, and time. When you say, we'll live somewhere else, you're really saying, we'll rebuild Earth's life support from scratch, inside a bubble, and it has to work non-stop. That's not just hard, that's borderline absurd on the scale of millions of people. Now let's zoom out to something even bigger than asteroids, the sun and the space weather it throws at you. You might think of sunlight as warm and gentle, but the sun is also a storm machine. It can launch giant eruptions of plasma and magnetic fields called coronal mass ejections. When those hit Earth, your magnetic field usually takes the punch. You might get beautiful auroras, and sometimes you get disruptions to satellites, radio, and power grids. The key point is this: even here, on your home planet, you can feel the sun's moods. Now imagine living in a world without a strong magnetic field and a thick atmosphere. That's not a someday problem. That's an everyday survival issue. This is why missions that study the sun matter for your future, even if they don't look like colonization. NASA's Parker Solar Probe has flown closer to the sun than any spacecraft before, sampling the solar wind and helping scientists understand how the sun's outer atmosphere behaves. The European Space Agency and NASA's solar orbiter is also studying the sun from different angles, trying to connect what we see on the surface to what blasts outward into space. NASA Parker Solar Probe, ESA Solar Orbiter. These missions are like weather satellites for a star. They help you predict the kind of radiation environment that makes deep space so dangerous. And here's another loop to keep in your mind because it will matter later. Even if you solve radiation with better shielding, you still have to solve what radiation does to your cells over years, not months. That story is not finished yet. We have data, we have clues, but we do not have a clean, confident answer for long-duration human life far from Earth's protections. Now let's talk about the part of space exploration that actually gives you hope without lying to you. You don't need to physically go to every place in the universe to learn its secrets. You can reach out with light. This is where telescopes become your true starships. Hubble, launched in 1990, changed how you see the cosmos. It showed galaxies as they were billions of years ago because looking far away also means looking back in time. Then the James Webb Space Telescope, launched in 2021, started taking infrared views that push even deeper, revealing early galaxies and the chemistry of distant worlds with a clarity we never had before. NASA and ESA, Hubble, NASA, ESA, CSA, Webb. And those discoveries do something important to your brain and your heart at the same time. They remind you that you are made of stardust in the most literal way. The carbon in your cells and the oxygen you breathe were forged in stars. The heavier elements in your blood and bones were built in ancient stellar explosions. You are not separate from the universe. You are the universe in a form that can ask questions about itself. General stellar nucleosynthesis background supported by decades of astrophysics. A common summary appears in many NASA educational resources. That's the human connection piece, and it matters because the "we can't leave Earth" message can sound depressing if you only hear it as a closed door. But it's not only a closed door, it's also a spotlight. It tells you where your real mission is, understand your home, protect it, and explore the universe with the tools that actually fit the rules of physics. Now you might be thinking, okay, fine, interstellar travel is brutal, but what about spreading out just within the solar system, the Moon, Mars, maybe icy moons like Europa or Enceladus? Isn't that still leaving Earth? Yes, in a limited way, you can extend human presence. You can build outposts, you can do science, you can learn how to live in harsh places, but a full escape from Earth where billions of people can simply relocate, that's a different claim. And when you measure it against the real constraints, radiation, gravity, ecosystems, energy, and time, it starts to look less like a plan and more like a story you tell yourself when Earth feels complicated. And I get why the story is tempting. Earth can feel messy. Politics, conflict, disasters, noise. Space looks clean from a distance, looks quiet, like a reset button. But space is not a reset button. Space is the hardest environment you will ever meet. It doesn't care about your dreams. It doesn't compromise. It doesn't forgive mistakes. Even your nearest new homes are worlds that are trying to kill you every second you're there. And here's another open loop to hold on to because it's one of the strangest facts of all. Even if you built the perfect ship and solved every engineering problem, the universe still has a way of limiting you that isn't about rockets at all. It's about thermodynamics, it's about heat, energy, and a one-way direction to time. That sounds abstract, but it ends up putting a ceiling on what any civilization can do, no matter how smart it gets. We're going there next. Let's talk about something that doesn't get mentioned enough when people dream about vast cosmic empires. Entropy. Entropy is a concept from thermodynamics, the branch of physics that deals with heat and energy. In simple terms, entropy measures disorder. And the second law of thermodynamics says that in any closed system, entropy always increases over time. Things naturally move from order to disorder. A hot cup of coffee cools down. A building crumbles if you don't maintain it. Energy spreads out and becomes less useful. This might seem like just a physics detail, but it has profound implications for life in the universe. Every time you do anything, move, think, build, communicate, you use energy. And every time you use energy, some of it becomes waste heat. That heat has to go somewhere. On Earth, this isn't usually a problem because you have a whole planet with atmosphere and oceans to absorb and radiate that heat away. But on a spacecraft or a small enclosed habitat, heat management becomes critical. The International Space Station has massive radiator panels to dump excess heat into space. Without them, the station would overheat from all the electronics, human bodies, and sunlight hitting it. As you scale up to larger habitats or faster propulsion systems, the heat problem gets worse. Nuclear reactors produce enormous amounts of waste heat. High-energy propulsion systems do too. You can't just open a window in space, you need radiators, and bigger radiators mean more mass, which brings us back to the rocket equation problem. But entropy affects more than just engineering. It affects the long-term fate of the entire universe. Current observations suggest the universe will continue expanding forever. Galaxies will drift apart. Stars will eventually burn out. Given enough time, trillions upon trillions of years, all the stars will die, all the black holes will evaporate through Hawking radiation, and the universe will reach a state called heat death, where everything is the same temperature and no energy flows anywhere. No energy flow means no life, no thought, no structure of any kind, just cold, dark, uniform emptiness. This is the ultimate wall, not just around Earth, not just around our galaxy, but around existence itself. The universe has an expiration date written into its fundamental laws. Now that's unfathomably far in the future, so it might seem irrelevant to your life or even to humanity's long-term survival. But it illustrates a key point. The universe is not designed for life. Life is a temporary, fragile phenomenon that arose despite the universe's tendency toward disorder, not because of any cosmic plan or purpose. And that brings us to a profound realization. You exist during an incredibly special window of cosmic time. Right now, the universe is about 13.8 billion years old. Stars are still forming. Galaxies are still visible across vast distances. The cosmic microwave background radiation, the afterglow of the Big Bang, is still detectable. Planets like Earth exist with liquid water and stable environments. This won't last forever. In a few trillion years, star formation will slow and eventually stop as the universe runs out of hydrogen gas. The night sky will grow darker as distant galaxies recede beyond the cosmic horizon. Eventually, even the longest-lived stars will burn out. You're living in what cosmologists sometimes call the stelliferous era, the age of stars. It's a brief moment in the universe's total timeline. Before this era, the universe was too hot and dense for stars or planets. After this era, it will be too cold and empty. You're here now in the sweet spot. And on this particular planet, in this particular solar system, conditions are just right for complex life. Earth orbits in the habitable zone of a stable, long-lived star. It has liquid water, a protective atmosphere, a magnetic field, and plate tectonics that recycle nutrients and regulate the climate over geological timescales. This isn't common. Most planets are too hot, too cold, too massive, too close to their star, or orbiting stars that are too unstable. The Kepler Space Telescope, which operated from 2009 to 2018, discovered thousands of exoplanets. It showed that planets are common, but Earth-like planets in stable, habitable orbits are rare. NASA Kepler mission results. The TESS mission, the Transiting Exoplanet Survey satellite launched in 2018, continues this search, finding more worlds and helping scientists understand how many might be potentially habitable. But potentially habitable just means liquid water might exist on the surface. It doesn't mean breathable air, edible food, or protection from radiation. It doesn't mean a working biosphere. NASA TESS mission. Think about what a working biosphere actually is. It's billions of years of evolution creating an interconnected web of life. Plants produce oxygen as a waste product of photosynthesis. Animals breathe that oxygen and exhale carbon dioxide, which plants use. Decomposers break down dead material, returning nutrients to the soil. Predators keep prey populations in check. Pollinators help plants reproduce. Mycorrhizal fungi connect plant roots underground, allowing them to share nutrients and even chemical signals. This system is so complex that we still don't fully understand all its connections. Every time ecologists study an ecosystem closely, they find new relationships they didn't know existed. And this complexity isn't just beautiful, it's functional. It creates stability. If one species declines, others can fill its role. The system has redundancy and resilience. You can't pack that into a spaceship. You can't recreate 4 billion years of evolution in a sealed tin can, hurtling through the void. Some people propose sending genetic information instead of living organisms. DNA sequences stored digitally, along with the technology to synthesize organisms at the destination. But who would build the bodies? Who would raise the children? How would culture and knowledge be transmitted? You'd be creating orphans in the most profound sense, beings with no connection to the life and history that created them. And this raises an ethical question that doesn't get discussed enough. Do we have the right to create human life in such circumstances? If you send people on a one-way journey to another star, they didn't choose that fate. Maybe the original crew did, but their children didn't. Their grandchildren didn't. You'd be condemning generations of people to live in a confined space, knowing they'll never see Earth, never breathe unfiltered air, never experience the planet their species evolved on. Is that fair? Is that ethical? What if they want to turn around? What if the mission fails and they're stranded in deep space? light years from any help. These aren't just philosophical questions, they're practical concerns that would need answers before any such mission could be morally justified. Now let's bring this back to something you can touch, the International Space Station. It's humanity's most successful long-term presence in space, continuously occupied since November 2000. Astronauts from dozens of countries have lived there. It's taught us enormous amounts about living in microgravity, about closed-loop life support, about human physiology in space, but it's also shown us how hard it is. The station requires constant resupply from Earth. Equipment breaks regularly and needs replacement parts. The station itself is aging, with some modules now over 20 years old. NASA and its partners plan to deorbit the ISS sometime around 2030, crashing it into the Pacific Ocean in a controlled re-entry. After more than 30 years in orbit and hundreds of billions of dollars invested, the ISS will fall into the ocean. It can't last forever. Nothing does, especially in the harsh environment of space. And the ISS is only 400 kilometers up. That's closer than many people drive to work each day. It's not even really in space in the sense of being beyond Earth's influence. It's still within Earth's magnetosphere, still experiencing some atmospheric drag, still close enough for emergency evacuation if needed. Compare that to Mars at its closest approach, 55 million kilometers away, or Alpha Centauri, 40 trillion kilometers away. The difference in scale is incomprehensible, and every kilometer adds difficulty exponentially, not linearly. Let me give you another perspective on this. The fastest human-made object ever is the Parker Solar Probe. At its closest approach to the Sun, it reaches speeds of about 190 kilometers per second. That's insanely fast, over 680,000 kilometers per hour. But even at that incredible speed, it would take this probe over 6,000 years to reach Alpha Centauri. Think about that. The fastest thing humans have ever built, moving at speeds we can barely imagine, would still take 60 centuries to reach our nearest stellar neighbor. And remember, that probe carries no crew, no life support, no shielding, no communication equipment beyond basic instruments. Adding all the systems needed to keep humans alive would slow it down dramatically. This is the universe telling you something. The distances are too vast. The energies required are too enormous. The timescales are too long. But here's the thing, accepting these limits doesn't mean giving up. It means being honest about what's possible and what's not. It means focusing your energy and resources on things that can actually work. You can explore the universe with telescopes and robotic probes. You can study other worlds without contaminating them. You can learn about the cosmos without leaving Earth. And you can take care of the one planet you know works. The one planet with forests and oceans and clouds. The one planet where children can run outside and breathe without a suit. The one planet that has already given you everything you need. There's a photo that matters, and you've probably seen it. It's called Pale Blue Dot, taken by Voyager 1 on February 14, 1990, from about 6 billion kilometers away. Earth appears as a tiny speck, less than a pixel, suspended in a beam of scattered sunlight. The astronomer Carl Sagan, who suggested Voyager take that photo, wrote about it. That's here, that's home, that's us. On it, everyone you love, everyone you know, everyone you ever heard of, every human being who ever was, lived out their lives. On a mote of dust, suspended in a sunbeam, every king and peasant, every creator and destroyer, every hero and villain, every civilization, every hope and dream, all of it on that pale blue dot. And beyond it, vast, cold, indifferent space. That image, that pale blue dot, should change how you think about Earth, not as a prison, but as a sanctuary, not as something to escape from, but as something to cherish, and protect with everything you have, because here's the truth that gets lost in all the excitement about space colonies and interstellar empires. Earth is not just your home by accident, it's your home because it's the only place in the known universe specifically built for you, and you were built for it. Every breath you take is calibrated for Earth's atmosphere. 78% nitrogen, 21% oxygen, trace amounts of other gases. Your lungs evolved for exactly this mixture at exactly this pressure. Go too high up a mountain, and you struggle to breathe because the air is thinner. The partial pressure of oxygen drops and your body can't extract enough of it. Above about 8,000 meters, you enter the death zone, where your body physically cannot adapt no matter how long you stay. You slowly die. Now imagine breathing in an artificial habitat where the mixture has to be manufactured and maintained perfectly every moment for years or decades. One malfunction, one contamination, one imbalance, and everyone inside could suffocate or be poisoned. Your body temperature regulation system evolved for Earth's conditions too. You maintain a core temperature around 37 degrees Celsius. When it's hot, you sweat, and evaporation cools you down. When it's cold, you shiver to generate heat. This works on Earth because you have air for convection and evaporation. In space, in a vacuum, heat management becomes incredibly difficult because there's no air to carry heat away from your body. You'd overheat from your own metabolism unless you had active cooling systems running constantly. Your immune system evolved fighting Earth microbes. It's been trained over millions of years to recognize threats and respond to them. In a completely sterile artificial environment, your immune system might weaken from lack of stimulation. Or if new, unexpected microbes evolve in the isolated spacecraft environment, your immune system might not recognize them until it's too late. Your circadian rhythm, your sleep-wake cycle, is tied to Earth's 24-hour rotation. Light and darkness signal your brain to produce hormones like melatonin that regulate sleep. On the ISS, astronauts experience 16 sunrises and sunsets every day as they orbit Earth every 90 minutes. This disrupts their sleep patterns. They use blackout shades and timed lighting to simulate Earth's day-night cycle, but it's artificial and imperfect. Sleep problems are among the most common complaints from astronauts. Even your sense of direction depends on Earth. Your inner ear contains fluid-filled canals that detect acceleration and orientation using gravity. In microgravity, this system gets confused. About half of astronauts experience space adaptation syndrome, basically motion sickness, when they first reach orbit. Your brain receives conflicting signals. Your eyes say you're floating, but your inner ear expects gravity. The result is nausea, disorientation, and headaches. Most astronauts adapt after a few days, but some remain sensitive throughout their missions. These aren't minor inconveniences, they're fundamental mismatches between your biology and the environment. And they demonstrate a simple truth: you were shaped by Earth, and Earth was shaped for you, through billions of years of coevolution. Let me tell you about one more problem that doesn't get enough attention: time perception and psychological duration. Humans are terrible at thinking long-term. Your brain evolved to worry about immediate threats: predators, finding food, shelter from weather. Even in modern times, most people struggle to plan more than a few years ahead. Saving for retirement is hard because it feels so distant and abstract. Now imagine a journey that takes not years, but lifetimes. Multiple generations born, living, and dying aboard a spacecraft, never seeing the destination. How do you maintain motivation and purpose across that span? How do you prevent social collapse, maintain discipline, preserve knowledge and skills? There are historical examples of long-term isolation in human societies. The Polynesians, who voyaged across the Pacific Ocean, spending weeks or months on open water, navigating by stars and ocean currents. But even those journeys had endpoints measured in human lifetimes. They could see their destination eventually. They could turn back if needed. And they traveled to islands that already had food, water, and breathable air. Antarctic research stations offer another comparison. Teams spend months in isolation during the Antarctic winter when it's too dangerous for planes to land or ships to approach. Psychological studies of these crews show predictable patterns: initial excitement, followed by adjustment, then a difficult middle period with conflicts and depression, and finally anticipation as the end approaches. But those missions last months, maybe a year. Everyone knows exactly when it ends. Everyone knows rescue is theoretically possible in an emergency. Everyone knows Earth is still there, still turning, waiting for their return. A generational ship has none of that certainty. You're born on the ship. You live your entire life in corridors and chambers. You die on the ship, never having seen a horizon, never having felt rain, never having stood under a sky. Your children and grandchildren face the same existence, and somewhere, generations down the line, your descendants might reach the destination, or they might not. The ship could fail, the mission could be abandoned, the destination might turn out to be unsuitable. Would people in that situation maintain their ancestors' purpose, or would they eventually ask why they're making this sacrifice for a distant goal they'll never see? There's a concept in psychology called temporal discounting. It means people value immediate rewards much more highly than distant ones. $100 today feels more valuable than $100 a year from now, even though rationally they're the same amount. This tendency is hardwired into human psychology. How do you overcome temporal discounting across centuries? How do you make people care about a destination their great-great-great-grandchildren might reach? Some people propose cultural and religious structures to maintain purpose. Turn the journey itself into a sacred mission with rituals and beliefs that bind each generation to the goal. Maybe that could work. But it also feels dystopian. Creating a society where questioning the mission is heresy, where individual desires are subordinated to a collective goal they didn't choose. And there's another question. What happens when they arrive? If the destination is habitable, they'd need to transition from a closed artificial environment to living on a planetary surface again. Skills and knowledge about surviving in natural environments might be lost over the generations. The travelers might have adapted to spacecraft life so thoroughly that they can't adapt back. If the destination isn't habitable, they'd need to build habitats there, facing all the same challenges as on the journey, but now with limited resources and no way to leave if things go wrong. Let's pull back and look at this from an even bigger perspective. Forget about humans for a moment and think about life itself. Life, as far as we know, requires liquid water, a source of energy, and organic chemistry. Earth provides all three abundantly. Liquid water covers 70% of the surface. Sunlight pours down constantly, captured by photosynthetic organisms and channeled into the food web. Organic molecules are everywhere, built and rebuilt in endless cycles. But in the universe as a whole, these conditions are rare. Most of the universe is empty space, far from stars, with temperatures just a few degrees above absolute zero. Most planets are lifeless rocks or gas giants. Most stars are too unstable, too hot, or too dim to support Earth-like planets in stable, habitable zones. The more we learn about exoplanets, the more we realize how unusual Earth is. Not unique, probably, but definitely uncommon. And even finding another Earth-like planet doesn't mean it has life. It just means it might have the conditions for life to arise. The origin of life itself is still a mystery. We know it happened on Earth roughly 3.8 to 4 billion years ago, not long after the planet cooled enough to have liquid water. But we don't know how it happened. Scientists have proposed various mechanisms: chemical reactions in hydrothermal vents, lightning strikes in primordial atmospheres, organic molecules delivered by comets or asteroids, but we haven't definitively proven how non-living chemistry became living biology. This is important because it affects the likelihood of finding life elsewhere. If life arises easily whenever conditions are right, then the universe might be full of it. But if it requires an incredibly unlikely series of events, then life might be extraordinarily rare, and Earth might be one of the few places in the entire galaxy, or even the observable universe, where it exists. We don't know which is true. We have a sample size of 1, Earth. Until we find life elsewhere or definitively prove its absence in places we've looked carefully, we're guessing. But here's what we do know. Complex multicellular life took a long time to evolve on Earth. Single-celled organisms appeared roughly 3.8 billion years ago, but complex multicellular life didn't appear until about 600 million years ago in the Cambrian explosion. That's over 3 billion years of nothing but microbes. Why did it take so long? We're not entirely sure, but it seems that multiple difficult steps were required. Eukaryotic cells, the complex cells that make up all multicellular life, likely arose from symbiosis between simpler cells. One cell engulfed another, and instead of digesting it, they formed a partnership. The engulfed cell became mitochondria, the powerhouses of eukaryotic cells. This might have only happened once in Earth's history. Endosymbiotic theory, widely accepted in biology. Then those eukaryotic cells had to learn to stick together and specialize into different types: muscle cells, nerve cells, digestive cells. That's another massive leap in complexity that took billions of years. Then intelligence had to evolve, not just survival instincts, but the ability to reason, plan, create tools, and eventually develop language and culture. On Earth, this only happened in one lineage, the primates that led to humans. Many other species are intelligent in various ways: dolphins, elephants, octopuses, crows, but none developed technology using civilization. Each of these steps might be incredibly unlikely. If any one of them has a very low probability, then intelligent life in the universe could be vanishingly rare, even if simple microbial life is common. This is sometimes called the rare Earth hypothesis, proposed by paleontologist Peter Ward and astronomer Donald Brownlee in 2000. They argue that while simple life might be common, complex life requires so many specific conditions: the right kind of star, a large moon to stabilize the planet's tilt, plate tectonics to regulate climate, a protective magnetic field, Jupiter-like planets to deflect asteroids, that Earth-like worlds are extremely rare. Ward and Brownlee, rare Earth. If they're right, then Earth isn't just your home. It might be one of the most precious places in the entire universe. A rare garden in a vast desert. And that brings us back to the central question: why would you ever want to leave? The answer, I think, lies in fear, not wonder, not curiosity, but fear. Fear that Earth won't last. Fear that humanity will destroy itself. Fear that we're putting all our eggs in one basket and a single catastrophe could end everything. That fear is understandable. It's even rational to some degree. Extinction events have happened before. Species die. Civilizations collapse. Nothing lasts forever. But here's the reality check. Spreading to other worlds doesn't actually solve the problem you think it does. Let's say, somehow, you establish a small colony on Mars. A few hundred or even a few thousand people living in sealed habitats, completely dependent on technology for every breath, every drop of water, every meal. Now Earth experiences a catastrophic disaster: nuclear war, asteroid impact, runaway climate change, whatever your worst fear is. Does the Mars colony survive independently? Almost certainly not. It would still depend on supplies, spare parts, and expertise from Earth. If Earth's industrial civilization collapses, Mars loses its lifeline. The colony would slowly fail as equipment breaks down and can't be replaced, as supply missions stop coming, as the genetic diversity of the small population leads to inbreeding and health problems. For a Mars colony to truly be independent, it would need to be completely self-sufficient. That means manufacturing everything locally: computer chips, medical equipment, spare parts, tools, materials. It means growing all its own food. It means having enough people to maintain genetic diversity and fill every specialized role a technological society needs. We're talking thousands, maybe tens of thousands of people with massive industrial infrastructure. Building that on Mars would be vastly more difficult and expensive than simply preventing or recovering from disaster on Earth. If you have the resources and technology to make Mars self-sufficient, you definitely have the resources to protect Earth or rebuild after catastrophe. Think about it practically. Even after a nuclear war, Earth would still have a breathable atmosphere, liquid water, organic soil, and partial ecosystems. Survivors could eventually rebuild. But Mars? Mars would still be a frozen desert with toxic soil, no breathable air, and deadly radiation. The habitats would be tombs once the life support failed. The same logic applies to more distant destinations. An interstellar colony would be even more isolated, even more dependent on functioning perfectly with no outside help, forever. One major system failure, one plague, one social collapse, and that's it. No rescue, no resupply, just death in the darkness between stars. So the backup for humanity argument doesn't really hold up under scrutiny. The only scenario where off-world colonies save humanity is one where Earth becomes literally uninhabitable, and we can't think of any realistic scenario where that happens, but Mars or spacecraft colonies somehow remain viable. Even if the Sun went supernova, which it won't because it's the wrong type of star, a Mars colony would die just as surely as Earth. If a gamma-ray burst hit our solar system, it would sterilize Mars just as effectively as Earth. If some exotic disaster made Earth uninhabitable, it would almost certainly affect the whole solar system. The real reason people talk about leaving Earth isn't practical survival, it's psychological. It's the pioneer spirit, the desire to explore and expand, the dream of new frontiers and fresh starts, and I get that. That desire is part of what makes us human. It's driven every great journey in human history. But there's a difference between exploring and abandoning. Between visiting and escaping, you can explore space without leaving Earth behind. In fact, that's exactly what you've been doing for over 60 years. Robotic missions have visited every planet in the solar system. Rovers have driven across Mars, analyzing rocks and searching for signs of ancient life. Probes have landed on asteroids, comets, and the moons of Saturn. Telescopes have peered billions of light-years into space, showing you galaxies as they were when the universe was young. And you've learned extraordinary things. You've discovered that Mars once had rivers and lakes, that Europa, a moon of Jupiter, has a liquid ocean beneath its ice crust that might harbor life, that Enceladus, a moon of Saturn, has geysers shooting water into space from a subsurface ocean, that thousands of planets orbit other stars, some possibly similar to Earth. The Cassini mission, which studied Saturn from 2004 to 2017, returned data that scientists are still analyzing years after the mission ended. It discovered that Enceladus has the right chemistry for life: liquid water, organic molecules, and energy from hydrothermal vents on its ocean floor. All the ingredients. We don't know if life is actually there, but it's possible. NASA Cassini mission findings. The Mars rovers, Spirit, Opportunity, Curiosity, and Perseverance, have revolutionized our understanding of the red planet. Curiosity, which landed in August 2012, found evidence that Mars had neutral pH water, the right temperature range, and all the chemical ingredients needed for life billions of years ago. Perseverance, which landed in February 2021, is currently collecting samples that a future mission might bring back to Earth for detailed analysis. NASA Mars rover missions. These robots are your explorers. They don't need food, water, or oxygen. They don't experience fear or loneliness. They can work in radiation that would kill a human in hours. They're far cheaper than crewed missions, and they can take risks that would be unacceptable with human lives at stake. And they're getting better. Each generation of Mars rover is more capable than the last. Future missions might include drones that can fly through the thin Martian atmosphere, submarines that can explore the oceans of Europa or Enceladus, and sample return missions that bring pieces of other worlds back to Earth for study. This is how you explore a universe that's fundamentally hostile to human biology. You send your sensors, your instruments, your robotic avatars, and you stay safe at home, analyzing the data they return, asking new questions and sending new missions. Some people find this unsatisfying. They want boots on the ground, human eyes, seeing alien vistas directly, the romance and adventure of human exploration. But consider what you'd actually experience as an astronaut on Mars. You'd spend most of your time inside a cramped habitat, breathing recycled air, eating monotonous food, performing routine maintenance on life support systems. When you did go outside, you'd be in a bulky spacesuit that limits your movement and visibility. You couldn't take your helmet off for even a second. You couldn't feel the wind because Mars's atmosphere is too thin to feel. You couldn't touch the soil with your bare hands. Meanwhile, a geologist on Earth working with rover data can examine rocks from Mars in extraordinary detail, using instruments that can identify minerals, detect organic molecules, and analyze chemical compositions. They can do this comfortably, safely, for years on end, without risking their lives. Which scenario actually advances science more? Which one actually satisfies curiosity more effectively? The human desire to physically go places is real and powerful, but it evolved in a context where going somewhere meant you could interact with it, live in it, become part of it. That context doesn't apply to Mars or anywhere else beyond Earth. You can't actually live on Mars in any meaningful sense. You can only survive inside artificial bubbles, fundamentally separated from the environment. So maybe the mature, wise approach is to accept that some places are for visiting, not living. Some frontiers are meant to be explored remotely. Some questions can be answered without physically being there. And maybe that's okay. Maybe that's even better, because it means you can explore the entire universe without putting human lives at risk. It means you can study other worlds without contaminating them. It means you can satisfy your curiosity without abandoning the one place that already has everything you need. There's another angle here that's worth considering: the environmental cost of space exploration. Launching rockets requires enormous amounts of energy and produces significant pollution. The space industry is growing rapidly, with companies like SpaceX, Blue Origin, and Rocket Lab launching rockets more frequently than ever before. Each launch burns tons of propellant, releasing carbon dioxide, water vapor, and other compounds into the atmosphere. Now, the current space industry's environmental impact is small compared to global aviation or shipping, but if space launch rates continue to grow exponentially, as some companies project, the impact will increase. And for what? So billionaires can take joyrides to the edge of space? So we can build colonies on lifeless worlds while Earth's ecosystems collapse? There's something deeply ironic about spending vast resources to make other planets habitable while we're making our own planet less habitable through neglect and exploitation. Climate change is real and accelerating. The global average temperature has increased by roughly 1.1 degrees Celsius since pre-industrial times, and the rate of increase is accelerating. Ice sheets are melting, sea levels are rising, Weather patterns are becoming more extreme. Ecosystems are shifting and collapsing. IPCC reports widely accepted climate science, and we have the technology to address these problems. Renewable energy sources like solar and wind are now cheaper than fossil fuels in many places. Electric vehicles are becoming practical and affordable. Carbon capture technologies, while still developing, show promise. Agricultural practices that restore soil health and sequester carbon are being demonstrated worldwide. The challenge isn't technology, it's will, it's prioritization, it's political and economic systems that resist change because it threatens short-term profits and entrenched power. Imagine if the hundreds of billions of dollars spent on space programs over the decades had been spent on protecting Earth's ecosystems, developing clean energy, restoring degraded landscapes, and pulling carbon from the atmosphere. Where would we be now? I'm not saying space exploration has no value. It does. It inspires people. It drives technological development. It helps us understand our place in the universe. It's given us critical tools like GPS, weather satellites, and Earth observation systems that help us understand and manage our planet. But there's a balance to strike, and right now that balance is off. We're dreaming about Mars colonies while rainforests burn. We're planning missions to distant stars while ocean ecosystems collapse. We're looking outward when we desperately need to look inward at ourselves and our relationship with the only home we have. Here's a thought experiment. If you spent just 1/10 of the energy and resources currently devoted to planning Mars colonies on rewilding Earth, restoring ecosystems, and developing sustainable technologies, what could you achieve? You could restore vast areas of forest, which would sequester carbon, provide habitat for countless species, regulate water cycles, and support human communities. You could clean up the oceans, removing plastic pollution and restoring coral reefs and fish populations. You could develop closed-loop industrial systems where waste from one process becomes input for another, eliminating pollution. You could redesign cities to be green, walkable, and integrated with nature rather than separated from it. Earth could become not just livable, but flourishing. A garden planet where human civilization and natural ecosystems exist in balance, each supporting the other. That's not naive optimism, it's practical reality. We have the knowledge and technology, we just need the collective will to do it. If you made it this far, make sure to subscribe to the channel and give a like. And check out this other video at the left side of the screen. How small are we inside the Milky Way? In this video, we explore our true place in the galaxy, from the staggering number of stars to the mind-blowing distances that separate them. See you there.